Hello, everyone. So this week we're going to take us a bit to talk about an important analytical technique that we're going to be using throughout this semester called mass spectrometry. Okay. This is something that we're going to actually be using to analyze our samples after we perform our in-home lab experiments. So this week is really going to be kind of like a lecture week where I give you the background information as well as the tools to analyze mass spectrum. So first of all, just a little bit of background here. Mass spectrometry is really good at determining the molar mass and even the molecular formula for an unknown compound. Broadly speaking, and we'll see the breakdown of the instrumentation here in a second, but you take a sample and it's actually vaporized, turned into a gas, and then ionized, means it's given a charge, and then it will undergo fragmentation in this instrument. And by looking at those fragments, we can piece together what the molecules are. So it's actually the masses of these individual ions that are detected. So just sort of a breakdown of what's going on here in terms of our sample. So again, you sort of inject your sample into the instrument and it's vaporized, meaning again, just converted to a gas. We can do that with the heat source. And then it's bombarded with electrons, okay? And we'll see in a second how this gives it the charge that it does. But the bottom line is that this will charge those particles, okay? That's really important for how mass spec works. The ions are then accelerated into this tube, and then they hit this curved part here, which has a magnet in it. Because these particles are charged, that magnet will deflect the particles, but it does so based on their mass, okay? So the lighter particles, or least massive particles, will be deflected the most, whereas the heaviest particles, or the most massive, will be deflected the least. And so based on where on this detector those particles hit, we can measure their mass, right? So again, the heaviest hit on one side, the lightest hit on the other, and anything in between will hit in between. So based on where these charged particles are hitting the detector, the machine knows what their mass is. And so you get this little plot at the end of the day where on the one axis you have atomic mass, and on the other axis you have the relative abundance, or how many of those fragments actually made it to the detector. And we'll talk in the next lecture about what makes a good fragment that's going to get to the detector versus a bad fragment, all that good stuff. For now, just bear with me on that. But the bottom line is that we can sort of tell based on where that detector hit what the mass of those particles are, okay? So what happens when these particles are hit with these ionized electron, or this beam of electrons, is it creates what's known as a radical cation. That electrons, the electrons themselves don't actually stick to the particles. What they do is they'll knock an existing electron off of the molecule. Okay, so that leaves a radical cation, right? So we got rid of this negatively charged electron. And so what we're left with is a positively charged particle that also is a radical because one of those electrons are no longer paired, okay? This intact species is what's known as the molecular ion, or the parent ion. That means that we haven't lost any atoms. There hasn't been any fragmentation that's occurred. Okay, the molecular ion is going to be really important. It's going to be one of the first things we look at when we look at a mass spectrum. There's a ton of information there. All right, but importantly, hit this particle. This is a normal old, let's just call this even ethane. We vaporize it and then we bombard it with this beam of electrons. And what that beam of electrons is doing is it's going to end up kicking an electron off of that ethane molecule, leaving us with a radical cation. Again, very important that it has a positive charge associated with it now. And then, so sometimes that molecular ion, that intact radical cation, will make it all the way to the detector. Often what happens though, is it actually further fragments into your radical cation will fragment into just a radical and a cation. right? So 1/2 of this molecule will end up accepting that 1 electron. That's what we see here. And that leaves the other one with a positive charge, okay? Again, this is really important because this charged particle, it's only going to be the charged particle that makes its way to the detector. So when we have a fragmentation, the radical doesn't actually do anything. It kind of just flies off into the machine. The carbocation portion, or the cation portion, the one with the positive charge, is what makes its way to the detector. And what the detector is really measuring is actually the mass to charge ratio. So M is the mass divided by the charge. For small molecules, for small organic molecules, like what we're going to be doing in this lab, the charge is almost always +1. So it's really just the actual mass. When you get to like large biomolecules or something like that, the charge can actually increase, you know, more than 1 electron can be knocked off of a single biomolecule, something really large. And so this becomes more important as we go. As you get larger, rather. But for most small molecules, it'll only ever get a charge of +1 on it. So what you see on the detector is really the actual mass of those fragments. And again, the neutrally charged or radical fragments aren't going to be detected at all. They don't get deflected by that magnetic field, etc. Okay, so if we had, for example, let's take methane. We bombard it with electrons, we get our radical cation, our molecular ion. That's going to have a particular m/z. Again, that's because z is just +1 here. Again, that's what it's going to be for every molecule that we deal with in this class. But yes, nonetheless, so this would be one peak that we see on our detector. And then we'd also see a fragmentation peak corresponding to the breaking of our radical cation into the hydrogen radical, which we won't see on the detector, and then this fragment, right? And notice, because we've lost this hydrogen to this fragmentation, our m/z has decreased by 1, because hydrogen weighs 1, okay? If we lost more hydrogens, again, you would expect your mass to decrease by 1 for each hydrogen loss. All right, so now when we look at a mass spectrum, again, what you're sort of seeing is the relative abundance of each of these fragmentation peaks. We'll talk about what makes an abundant, you know, what makes something more likely to be abundant. For the most part, you don't really know just by looking at a molecule too much about how it's going to fragment. There are some key things that we'll learn to look for. But for the most part, it's not something that you're going to look at and know exactly all the fragments that appear. It's something that we look at the data and understand, okay? Important terminology, though, is base peak of your spectrum. You'll notice that this is relative abundance. The abundance is always measured relative to the base peak or the tallest peak in the spectrum. So whatever the tallest peak in the spectrum is, it automatically gets 100%, and everything else is measured relative to that, okay? So in this case here would be our molecular ion, right? The m/z corresponding to that whole molecule. And this is the one with 1 hydrogen loss. Notice over here, we do have what's called the m+1 peak. We'll talk about that here in a second. So when you're looking at your mass spectrum, you're going to look all the way to the left to figure, or no, that's not true. All the way to the right to see your molecular ion, that M+ peak. But you're going to ignore the tiny, or you're not going to ignore, we'll figure out what to do with it here in a second. But you're just going to note that there's always going to be a little tiny baby peak that's right next to it, 1 unit above it. And that corresponds to the tiny amount of sample that has those higher mass isotopes, which are rare. Okay, in the case of methane, the base peak and the parent ion or the molecular ion are the same thing. That's not necessarily going to be the case, but for this simple molecule, it is. When you have something larger like pentane, so first of all, take a second, see if you can't point out where my molecular ion peak is on this and where my base peak is on this spectrum. Okay, and again, you're not going to know right off the bat that pentane is going to fragment like this. This is something that you were just going to have to get comfortable with looking at these spectra, but we can get some information from it. First of all, this one right here would be my molecular ion peak. This one, this tinier one, is the M+1 peak. And again, we'll talk about what to do with that here in a second. And then what's going to be my base peak? Again, that's simply just the largest peak in the spectrum. So this is my base peak. Okay. And again, we'll talk about fragmentation and stuff here in a later lecture. For now, we're just sort of worrying on being able to identify these key things from these spectra. And notice that our molecular ion peak will correspond to a mass M/Z of 72, which is the mass of a pentane. All right, so again, that tells you the molar mass of your compound. Okay, now something that's important to remember, again, what's mass spec good for? Two things, determining the molar mass or the molecular mass of a compound, and also we can get the molecular formulas of a compound, okay? So let's talk about the molecular formula here for a second, because I think that seems like a harder one. It's important to remember that not every molecular formula is possible, right? So for saturated compounds, let's just talk about saturated hydrocarbons real quick. They will always have this carbon or this sort of molecular formula pattern where the number of carbons is, if you have N carbons, then you have 2N plus 2 hydrogens. And that might not seem like all that much information, but you can rule out a lot. So for example, you would never have something that would be this molecular formula. Just doesn't exist, right? I mean, you could go on to infinity, basically because there's a certain architecture that we've talked about. Carbon likes to have 4 bonds, hydrogen likes to have 1 bond, etc. You can't just have any old molecular formula. They follow these pretty strict patterns. And especially if we're going to talk about a saturated molecule, saturated organic molecule. What do I mean by saturated? Meaning there are only single bonds in there. Then it's even more straightforward. So let's look at these real quick. So carbon is N, and hydrogen is 2N plus 2. And we can convince ourselves, I like to just convince myself of this type of stuff by looking at simple molecules. So let's look at propane. We have 1, 2, 3 carbons, and then 3, 4, 5, 6, 7, 8, right? So C3, and then H is this 2 times 3 plus 2. It is indeed C3H8, okay? Notice that if we add a halogen in there, halogens behave a lot like hydrogens in the sense that they only like to have 1 bond. So this changes our formula from Cn to now 2N plus 1, and then that other hydrogen, or that other single bond, and it's not 2N plus 2, it's 2N plus 1, because that other single bond is going to be replaced by a chlorine, right? So again, if I wanted to take my simplified model here, I'll replace this hydrogen with a chlorine, and that fits the formula C3H7Cl. Okay, similarly, I mean, if it was a bromine, it's the same thing. So we have that same pattern here. Okay. Let's go on to what happens when we have a oxygen. Notice that we actually have the same formula in terms of the number of carbons and hydrogens. Cn and H is 2N plus 2. Let's see if we can convince ourselves of that real quick. Let's just draw a simple one. An alcohol, for example. This would work for alcohols or ethers, right? As long as they're all single bonds, carbons and hydrogens and oxygens. So I can go fill in C1, 2, 3, 4, so that's C4. So then how many hydrogens should I have? Just based on the formula? Should be H10. And let's just convince ourselves. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the one that's actually bound to the oxygen. So C4H10O. Now, it does change to CN2N plus 3 if there's a nitrogen. Let's see if we can't convince ourselves of why that is. Because if I have a nitrogen here, it has to have 3 bonds. So that means there would have to be 2 hydrogens attached to it. And that's how I get my C4H should be 2N plus 3. So 8, 9, 10, 11. N. Let's just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So again, it's kind of like, it seems like there's just this infinite amount of possibilities and things are going to seem very overwhelming. First thing to do is just go back to these really simple formulas here. Make sure that your molecule, your molecular formula fits into one of these and you're good, right? And if we do add a degree of saturation, meaning we're going to have a molecule that contains a single double bond, that changes things a little bit because by basically removing 2 hydrogens from all the above formula. So now instead of CnH2n plus 2, it's just CnH2n, CnH2nO, CnH2n plus 1 with a nitrogen again, because that nitrogen has 3 bonds. And then again, the chlorines and the bromines behave like nitrogens. So instead of being 2N, it's got to be 2N minus 1 because we have that single bonded halogen. And again, let's just pick an oxygen for an example so we can convince ourselves of this. We'll do an aldehyde. This has this has 3 carbons. So that means that it should have 6 hydrogens. Let's just see, 1, 2, 3, 4, 5, 6. Okay. Of course, you can get more complicated by having compounds that have triple bonds or multiple double bonds, etc. But for the most part, we're going to be dealing with relatively simple molecules. So these are really good starting points. You know, if things get crazy from there, sure. But these are great starting points to make sure that your molecule just fits these simple formula. Okay, and then lastly, when we're talking about the mass here, we're talking about single elements that are hitting, or single molecules that are hitting these detectors, right? So usually when we were talking about calculating molar mass, we would use the atomic masses from the periodic tables, which are the molar masses. They're an averaged over a whole mole, or 6.022 times 10 to the 23rd atoms. Here you have like a compound that has only 4 carbons hitting that detector. So you're not going to have some decimal place number. It's going to be a hard, fast atomic mass corresponding to just the number of neutrons plus the number of protons. For the most part, these are just these simple masses that you're going to use to determine the mass, or the m over z of your fragments, right? So for hydrogen, the atomic mass is 1 atomic unit. Carbon is 12, nitrogen's 14, oxygen 16. When we get to the halogens, the different isotopes are way more abundant. So for example, carbon, 99% of the carbon in the world is carbon 12. There is a small amount that's carbon 13. When you're talking about chlorine and bromine though, there's actually a significant amount of both of those isotopes that exist. So we have to pay attention to both of those masses. There's going to be a special lecture on the end specific to the halogens, so don't worry too much about that. But nonetheless, so basically it's pretty straightforward. If we're going to try to find the molecular ion m over z for something like, let's say, ethanol, it's just going to be, how many carbons do I have? 2 times the atomic mass of carbon plus how many hydrogens do I have? Well, total there's 6 times 1 plus how many oxygens do I have? 1 times 16. So the m over z of this parent ion will be 46. Okay, we'll specify it's the parent ion. Okay, so calculating the m over z, or the mass of parent ions, is very trivial using these masses here. Okay, so your first step is going to be to build a simple spreadsheet calculator to help you calculate the mass of any fragment using these masses here.